We'll go ahead and get started. Okie doke. All right, so we're going to finish up today then by talking about modern day climate change. And so when I say contemporary climate change, what I'm talking about is climate change that's happened primarily, let's say, since the Industrial Revolution, or specifically, we've seen a lot of this in the last 60 years or so. Probably from about 1960, we really start to see a significant increase in the temperature of Earth. And so the goal of today really is to help you to better understand what is happening with climate change, how we can talk about it. I think is also very important to how we can talk about it to other people who may not have as much of a background in science as we all do, and to keep in mind that this is really important for society and for the world in general, that we are able to understand and to explain what's going on. So we're going to kind of go through the different lines of evidence here to indicate that the Earth is warming, because I want to take an approach to this very much like, what are some of the things that people will say who don't believe in climate change? What are some of the arguments that they will make, and how can we respond to those? And so one of the arguments that people will make, and you don't actually hear this very often, I think most people by this point in time have accepted that the Earth is certainly getting warmer, but people will say, well, how do we know that the planet is warmer, right? And so we'll talk about that first. Well, the first thing is that we have to remember that we have a very long record of climate change on Earth. In the last couple of classes, we've talked about the fact that we see evidence of climate change in the last 5 million years, right, with ice ages, and those in fact are certainly climate change. If we look at what we would consider to be like the instrumental record, so what is available to us that has been measured by instruments, and so data that is not a proxy. And again, remember, proxy data would be something like oxygen isotopes, tree rings, for example. Hang on, let me make sure this is actually recording. Okay, it is, just to double check. Okay, so this is actual data recorded with actual instruments. And so here is a graph that illustrates to us climate change since 1880-ish or so, and that's basically where we start to have instrumental data. And so you will see often a lot of data that begins at 1880 and then goes to the present. The way that this figure works, let me explain a little bit to you, because this is something that you, again, will see very often. You'll notice that there are no numbers in terms of 80 degrees or 90 degrees or 100 degrees. Instead, what it says is anomalies in degrees Celsius relative to 1901 to 2000. And so often climate change is represented as what is the temperature of the climate now, right, of the Earth now, relative to the average in the previous century. And so that's where we're getting that 1901 to 2000 data from. And so that is the average temperature of the 20th century. The average temperature of the 20th century then is going to be represented by this line that is running horizontally through the middle of the figure at 0, 0. So if the temperature of the year, let's say 2018, is exactly the same as the average temperature between 1901 to 2000, then your point would be on that line exactly. If it's a higher temperature, it's going to be above the line, like we see on the right-hand side. If it's a lower temperature, it's below the line. And we often see data like this as anomalies relative to that. Usually that's the previous century. So this is all of that data since 1880, again, relative to the average of the previous century. And so you can see that there was a period in time in the late 1800s and the early 1900s till about 1930 or 1940, when it was actually cooler, again, average temperatures relative to the previous century. But when we start to get into the 1940s and we really start to see this take off around the 1960s or so, that average temperature starts to increase relatively dramatically. And so we can see it going up and up and up and up. It's flattening off a little bit here in the 2000s in this particular diagram. But that temperature then from at least probably 1970-ish or so is warmer than it was in the previous century. And so we see that in the record. It seems to be pretty obvious. Now, another thing, though, that's important in science is that, we never want to make any kind of hypothesis or assumption based on a single trend, a single data source. And so it's important that we're able to see this everywhere and not just in one set of data. And so this is the same graph. It looks a little bit different, but it's basically showing you the same information from 1880 to probably about 2015 is where this ends or so. Again, same thing with temperature anomaly, hotter than the average and then lower than the average. And this is 4 sets of data. So in red, we've got data from NASA Goddard, which is in Maryland. Blue is the Hadley Center for Climatic Research. We've got NOAA, which is the National, I think it's Oceanic and Atmospheric Organization. So they manage a lot of the climate data, most of it comes through NOAA. And then in purple here is the Japanese Meteorological Agency. So what is important about this is that if we look at all 4 sets of data, all of those trends are the same. Now, there are certainly places where they are not exactly the same. And so there are certainly places where the average temperature for that year may vary just a very minor amount, right? But what we see here is basically that this is very consistent. And the numbers are consistent, but also probably more importantly, is that the trend is consistent. So all of these data sets here are repeating the trend that we see in this original data, and this is NOAA's data. It looks exactly like what we see in the other 3 trends as well. So it's confirmed. And again, it's really important in science that we confirm trends, you know, with more than one data set. We have to make sure that they're repeatable, right? That's part of the scientific process. If NOAA had one trend and everyone else had a very different trend that illustrated that it wasn't warming at all, then that would be something that we would consider, oh, well, probably there was something wrong with that data. So we have multiple trends indicating the same thing. It's not just one set of data. And if we look at the last 10 years, if we look at average temperatures for the last 10 years, what we see is that the average temperature on the planet has continued to rise each year. In fact, the last 5 years have been the hottest 5 years on record. And again, on record means we're going back to 1880. Like 2016, 2017, and 2015, I think, like 15, 16, and 17 were each progressively warmer than the next. And we don't necessarily see that every year, but in general, the temperature is increasing. And so you can see last year, 2019 was the second warmest temperature ever, second warmest year, average temperature on record. 2016 has been the hottest year on record ever. According to a NOAA analysis that I was looking at yesterday, there's a 99.9% chance that 2020 will be among the top 5 warmest years. So it's very likely to continue in that trend. And there's about a 65% chance that it would be the warmest year since the record began in 1880. So it's not, it doesn't appear to be a fluke, again, because we see this consistently if we look at the data. Now, one of the ways that you often see climate data illustrated, and I wanted to show you this because this is very common, and again, this is data from NOAA. You'll often see it illustrated on a global map using a color scheme. We should, at this point, be kind of familiar with that color scheme where red is high and blue is low. We've done it with topography before. We've done it with the water, you know, the ice actually on Mars. We looked at that. So what we're looking at here is if something is very red, if it's a bright red color, then that means the temperature at that particular time was the warmest recorded on record. If something is blue, it was the coldest recorded on record. White tends to be near average. And if you see areas that are gray, those areas are where we don't have any kind of data. So we don't usually get a lot of data from the poles in particular, not a lot of temperature stations down in Antarctica. So I just picked one of the most recent ones that I could find on NOAA's webpage. And so this was August of 2020, so just a few months ago. And what you can see is that if we look kind of at the overall color, what we can see is that it's mostly pink and red. There are certainly areas where the temperature is near average, right? We've got some here, we've got some down here, parts of Europe, and maybe even just a teeny weeny bit of Russia over here is about average, even a little bit in the United States. But everywhere else basically is either much warmer than, according to the scale here, much warmer than, or the warmest recorded. And every month that we look at this data, we see similar trends. So you would see it no matter if you're looking in the summer. I could have shown you a period from January to, let's say, June. It would still look the same way. And so we continue again to see that trend of really warm periods, really warm areas on the surface of the Earth. So in case you see this again, which you probably will at some point, it's a very popular way to illustrate how climate change is happening. You'll know what you're looking at. But we see this no matter what period of time we're looking at. So another thing that's important to us when looking at the data is to make sure that we are looking at all of the data and not just kind of nitpicking a small part of time to say that this is what's happening in this amount of time, which is one of the ways that people tend to actually make science very bad is when they do that, when they take a large data set and they pick a small part of that data set and they say, okay, well, look at what is happening here. That must mean that this bigger, broader thing is happening. And so we don't want to extrapolate broadly without having all of that information. And so this climate change that we see, if we look beyond 1880, because again, that's not very long geologically speaking, if we go back further in geologic time, this takes us back to the year 300, we can see that the climate has changed over time. We looked at diagrams like this last week together, illustrating the ice age. Basically, you can see that a little bit here. Well, not really actually, but you can see the medieval warming period and you can see the little ice age. So you can definitely see that there have been fluctuations in temperature over, at least in this particular period in time, back to the year 300. So this increase that we're seeing right now, right, is substantial compared to what we see in this record. If we go even, oops, sorry, wrong way. If we go even further back, and so here we can see the ice ages that I just mentioned a minute ago, looking back to about 600,000 years ago, we can certainly see those changes, and the fact that those changes are very cyclic, right? They are not random changes. It's warmer and then it slowly gets colder, and then it very quickly gets warmer and it slowly gets colder. And as we said last Thursday, this happens over periods of about 100,000 years, or at least it's been happening that way for at least the last million years. And so there's a trend, right, to that climate change. We can see that the climate has changed substantially over that period of time. But again, if we look here at where we are today, that is a significant increase compared to what we have seen over time, right? If we look at the next warmest period in time, it's either probably about 300,000 years ago or a little before 100,000 years ago. But that temperature there is substantially lower than where we are today. So again, comparing this to a much bigger trend, this does check out that what we're seeing here is different, but is certainly happening compared to climate change over time. So it's pretty obvious that the planet is getting warmer. And like I said a minute ago, I don't think that's a thing that is super contentious for most people, but what is more contentious is what is causing the warming. Is it anthropogenic or is it natural cycles? And you'll hear natural cycles come up a lot. So let's look at that in a little bit more detail. First, is there a connection between temperature change and CO2 change? Now, as geologists, we know this answer to be true because we have used CO2 as a proxy for reconstructing climate change in very, very ancient parts of geologic time. But I think you can make the argument if you wanted to try to explain to someone how we know this. I think you can do it by looking at a few graphs indicating what has been happening recently. And so this is a global temperature and carbon dioxide graph. If we want to show that there is a correlation between temperature and carbon dioxide, we need to either look at the two of those on the same graph, or we need to have two individual graphs, one illustrating temperature, one illustrating carbon dioxide, that we can then compare, that are on the same time frame, same kind of scale, so we can make those comparisons. This one has both on one. So the carbon dioxide is the red line and global temperature is the blue line. And this again is going back to the beginning of the instrumental record, so about 1880. And if we look at temperature change, you can see that that is not a straight line, right? Because we do have variations in temperature every year. It doesn't necessarily go up, 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 right? It goes up and down a little bit, up and down a little bit, but the overall trend is certainly an upward trend. And if we look at carbon dioxide since 1880, which we have a good record of as well, we can see that line, that trend, follows the trend of temperature increase relatively well. Particularly here at the end, you can see it's the same exact slope. Now, if the line for CO2 was at a lower slope, so if it was sloping a little bit lower, had a shallower slope, or had a much steeper slope, you might then be able to make the argument that there is not necessarily a direct correlation now, right, between the CO2 and the temperature, but that is in fact not the case, right? We can see very clearly that it follows along relatively well. And again, we go back further into the geologic record and we see the same correlation between CO2 and between temperature. Here we're looking on the top diagram, this is the temperature diagram. And on the bottom diagram, this is the CO2 diagram. And so again, this is going back 600,000 years. This is the figure that's illustrating the ice ages. And so the ice ages, right, which are very obvious, have CO2 patterns that are nearly identical. So when we see a peak interglacial period like this one here at about 300,000, I don't know if you can see my pointer, but I'm pointing to the one right at 300,000 at the top here. If we go down to the bottom, we can see 300,000 years ago, we had a relatively high level of CO2 compared to, for example, what it was maybe 270,000 years ago or so, as it slowly decreased, and that took us into another ice age. So there's a very strong correlation between CO2 and temperature change. And again, we see this back way beyond 600,000 years. Not necessarily something that I think you can argue relatively well that doesn't exist, because it's very obvious and we've seen it for a very long period of time. And again, another thing that's important is if we look here at the very, very end, so where we are today in the modern world, last probably decade or so in this little line here, is that it has gone up, 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 very much, right? It's very, very high. And we see the same thing in CO2. So this peak here in the temperature, sometimes it's referred to as a hockey stick, right? Because it's kind of a line and then boom, you put the little hockey stick there, corresponds exactly to what we see in CO2. So the patterns are exactly the same, and the patterns have been the same for a very, very long period of time. So one of the things that will come up the most with people who do not believe in climate change, or either do not believe that climate change is anthropogenic, meaning that it was, you know, a people problem, a problem that people created, is that they will argue that this is a natural cycle. And this is an argument that you see a lot, because if you look at a lot of these figures, like we have just done here, you can certainly tell, like, and we know that climate has changed in the history of the Earth. It's changed substantially. So if you know that, if you have that information, then it becomes very easy to say, oh, well, the climate of Earth has always changed. This is just natural. Like, I hear that probably more, I think, than anything else. The climate has changed always. This is a natural cycle. So how do we know then that this is not, in fact, a natural cycle? Well, one of the things that that tells us is, and there are two things in particular, but the first thing is that if we look at this, this is a very, very extreme, very, very drastic change that has happened over a short period of time. It is much more significant, and it is much faster. It has happened much more quickly than any previous cyclic change. So again, all we have to do is, if we look at something like the Ice Age figures that we've been looking at recently, going back 600, 700,000 years, where we can see these patterns of change over time, going from interglacial to glacial periods. And then suddenly we get to now, and that line basically goes straight up, right? It's a very, very, very rapid change. And there's nothing, at least, right, in the last 700 or 600,000 years that is anything like that. Most of the change, right, we typically do tend to warm up quickly, and then cool very slowly, and warm up quickly, and then cool very slowly. But the temperature and the CO2, this is actually a diagram indicating CO2, the CO2 levels in the past, again, the last 600,000 years or so, were really not above about 300 parts per million. And that was pretty consistent. And there hasn't really been a significant change in CO2 during the ice ages. So that interglacial to glacial period was basically about the same. It goes back and forth from 300 down to probably 200. But we look now at modern time, and what we see is that that number is significantly higher and is continuing to go up. This website here, I'll pull it up and see if it'll share with you. This website here shows us what the CO2 parts per million is in the atmosphere every day. It hasn't updated for today yet, but yesterday it was 413.59 parts per million. So that's a significant amount of CO2 in the atmosphere, and again, much higher than it has been in modern time. You can close this down. So you can always check that number. I think we broke 400 for the first time 2 years ago or so, and it continues to go up and up and up. That data comes from it's either Mauna Kea or Mauna Loa, and I can't remember which one. I think it's Mauna Kea, whichever one is the less active one. But because it is up high, right, it's a very high volcano, it gets a better reading in the atmosphere of CO2, and so we have daily records of that. So very, very significant change, nothing like we've seen in the past. But I think even a stronger argument in my mind about why this is not a natural cycle is because if this was a natural cycle, what we would see is completely the opposite of what we are actually seeing today. So what do I mean by that? Let's go back and look again at the last, this is 400 or 500,000 years or so, illustrating those ice ages. So we can see the interglacial and the glacial periods. So we came down from about, let's say, 100 and 120 maybe 1,000 years ago or so, started to cool, coming down into that last ice age. And so then we have been coming out of the ice age since probably about 17,000 years ago or so. That's probably the end of the last glacial period. And if we look then, if we compare where we are today, and so if you can't see my cursor, I'm pointing to exactly where there's an arrow that says 1950. If we kind of look at that particular point there, that's where the numbers were in 1950. That is pretty consistent with what we see of the peak of the last 3 ice ages in terms of CO2 in the atmosphere. So that would indicate that that was probably about the end of that particular period, where we would start then to go back into a cooling trend to go into the next ice age. Because you can remember that heating is relatively quick, but then the cooling is relatively slow. And so we were at that peak, right, where we think cooling would start. But instead of going into a cooling trend, which is what would be indicated by the geologic record, right, that we would start to cool again and start to slowly go into another period of glaciation, and we have that problem to worry about. Instead of that, it has warmed dramatically. And so this is the opposite of the natural cycle. The natural cycle should be that we are going into another glaciation. That is what we've seen for the past 600,000 years. There's nothing to indicate that anything different should be happening if this is natural. And so the fact that the CO2 has increased and has decreased, or sorry, increased and has increased so dramatically indicates to us that this cannot be part of the natural cycle, again, because the natural cycle would in fact be going the other way, and it would be cooling on Earth and not heating. So this is certainly not a natural phenomenon. How do we know the CO2 is anthropogenic though? How do we know that this is CO2 that humankind has put into the atmosphere rather than some weird, strange, natural phenomenon? Like people will say, oh, volcanoes put CO2 into the atmosphere. It's maybe just, they're putting more CO2 into the atmosphere than is typical, right? So why is that not the case? Again, we have good data that we can look at that actually answers this question relatively well. I wish that scientists would do a better job of answering this question because it's not a complicated question. I think that it's actually relatively simple to explain how we know this, and for whatever reason, we don't do that very well, which is our fault, but I think we need to work on how to do that. The first way we know this is we have to think about what happens to carbon when it goes into the atmosphere, if it is natural carbon versus anthropogenic carbon. Now, natural carbon in the carbon cycle, when it goes into the atmosphere, no matter if it's from the oceans, if we're releasing it from plants, or if it's coming out of a volcano, that is released into the atmosphere directly as CO2. So the carbon has combined with oxygen to make carbon dioxide gas. So when carbon naturally goes into the atmosphere, it is already CO2, and we are adding pure CO2 to the atmosphere. Now, carbon that is anthropogenic, that is not coming from a natural cycle, like so, for example, burning fossil fuels. When we burn fossil fuels, what we are doing is not putting CO2 into the atmosphere, we are putting carbon into the atmosphere, so just the carbon itself. And so what then happens is that the carbon has to combine with oxygen to make carbon dioxide. So the oxygen doesn't come with it in tow, right? It has to combine and then and then it will become CO2 in the atmosphere. So if right, understanding that, right, how those two different carbons work, if more anthropogenic carbon is going into the atmosphere, then that means that some of the oxygen that is in our atmosphere is being removed so that it can combine with carbon to make CO2. So oxygen then should be decreasing, right? If there is an increase in anthropogenic carbon, then oxygen should be decreasing. This is something that we haven't been able to measure actually till relatively recently. And I think maybe this is one of the reasons people don't talk about it as much. I still am perplexed. But since, maybe 1990-ish, somewhere between 1990 and 1995, we were able to take measurements at a resolution that would be useful to us, because even though there's like 20 some odd % oxygen in the atmosphere, we are talking about very, 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 very small changes here, right? So we're not worrying about running out of oxygen, very small changes that were very, very difficult to measure. But we can do it now. And so what we see is if we look at when we have been able to start measuring this data, which again was around 1990, we see a decrease in oxygen in the atmosphere. And it's about the same increase, right? Or a relatively similar decrease, to the increase that we see in CO2. So again, that's indicating to us that oxygen is being taken out of the atmosphere, right? It's being removed from the atmosphere so that it can then combine with carbon to make CO2. And again, right, just to reiterate this, if this was natural carbon, we would not see a change in oxygen, right? Because everything would go into the atmosphere as carbon dioxide. So I guess if we actually did see a change in oxygen, it would go up as opposed to going down, but it would probably just stay the same because everything is already combined in those two molecules. So the decrease in oxygen indicates to us that this is certainly not natural CO2. We can also use isotopes, though, to make this come to the same conclusion. And again, this is something that you very rarely hear people talk about. It is a mystery to me about why we do not, because it's a very strong piece of evidence. And I don't know if it's because, people are like, well, not everyone knows what an isotope is. How do we explain this? But I really don't think it's that complicated. I think you guys, after having a semester of geology, could now explain what an isotope is, and I think make this case relatively well. So here we're focusing on carbon isotopes. We've talked a lot about oxygen, but there are different isotopes of carbon too. There's carbon-14, carbon-13, and carbon-12 are the most common. Carbon-13 prefers natural carbon, or I should say natural carbon prefers to be in the state of carbon-13, prefers that mass of isotope, whereas anthropogenic carbon tends to prefer carbon-12. So when we are burning fossil fuels, we are adding carbon-12 to the atmosphere. Everything else that happens naturally is adding carbon-13 to the atmosphere, okay? So again, in the same way that we looked for changes in oxygen, if we hypothesize that the additional carbon that is in the atmosphere now, and that has been going into the atmosphere for the last several decades, if that is because of fossil fuels, then we would expect to see the abundance of carbon-12 in the atmosphere increase over time relative to the abundance of carbon-13, okay? And that is exactly what we see. Now, this diagram is a little tricky to read because it's looking at what we call delta 13C. And so this is basically the ratio of carbon-13 to carbon-12. And it's kind of, they've got the axes a little bit backwards to make it go up as opposed to go down. So it makes better sense. It's a strange graph, but what is the easy explanation here is that we see that carbon-12 is going up in the atmosphere relative to carbon-13. And so again, because it is carbon-12 and not carbon-13 that is increasing, that indicates to us that this is carbon from burning fossil fuels, okay? So there is really no doubt, right? People will like to pretend or like to think that there is a little bit of doubt in our understanding of this, but there is no doubt that the carbon in the atmosphere is anthropogenic, and that we've been putting it there since, easily the Industrial Revolution. And so, again, I think like really obvious, really easy to make this argument. So it's been increasing since about 1970, since we started looking at it. One final way that we can argue that CO2 is anthropogenic is if we look at other greenhouse gases, they've gone up as well. So this is not just some unusual trend that we see in CO2. We do see the trend more strongly in CO2 than we do in the other gases, but you can see we've got methane here. Methane is the orange, and then nitrous oxide is in like a reddish color or either kind of a darker orange. But again, we see the same trends of those gases increasing since, 1940, 1950, just as we do with carbon dioxide. So it's not something that is this anomalous thing happening with carbon dioxide. It's not because people are breathing out more carbon dioxide or whatever, some, random things you will hear. This is very much, very clearly fossil fuel burning. So what happens then if we continue to put CO2 in the atmosphere at the rate that we are doing it now? So let me explain what you're looking at here. On the left, we've got a model. Remember, scientists use models a lot to make predictions about what's going to happen based on data that we have. And so in this case, we have a longish, right, instrumental record of temperature and a record also of CO2. And so that actual record is shown here in the black line. So those are recorded observations, in this case from about 1900 to, this probably goes to 2010, 2015 or so is when this probably ends. So the different colored lines here are lines that represent different hypothetical conditions. So the purple line is a model of high emissions, meaning that emissions of CO2 continue to increase over time, because we've been putting more and more CO2 in the atmosphere over time. So CO2 increases at a higher rate than we're putting it into the atmosphere today. The red line is what we call medium emissions model, and that indicates that this is probably what it would look like, what temperature change would look like if things stay the same and we don't do anything. We don't make it worse, but we don't make it any better. And then the blue line here is a low emissions model. And so this is a line that we really strive for. This is a line where we want to be. But this is a line that indicates that there would have to be significant change in our behavior in the way that we modify the environment. And so that we would have to decrease significantly the amount of CO2 that's going into the atmosphere. That was one of the accords of the Paris Accord, right? One of the things that the Paris Accord is really striving for is bringing down CO2 emissions to a more reasonable level so that temperature will still be increasing, but not as significantly as it would be otherwise. Because if you look at the y-axis here and the purple, the red versus the blue, right, the best possible scenario based on what we think could happen, still results in an increase in temperature of about 2 degrees by the year 2100, so into the next century. We're kind of on track, though, unfortunately, right now to have an increase that's more like closer to 3.5 or 4, or even if it gets worse, 4.5 degrees by the year 2100. And that's a substantial temperature change over time. That's certainly nothing to scoff about. This map over here on the right-hand side is illustrating that in a slightly different way, and also illustrates how climate change is not consistent everywhere, right? There are certainly parts of the globe that are more affected by climate change and others, very much in the same way that glaciers tend to form in the northern hemisphere as opposed to the southern hemisphere, because of the way that solar insolation is kind of works a little bit more in the northern hemisphere, is magnified perhaps in the northern hemisphere than it is elsewhere. And so this is a prediction of what it would look like between the year 2070 and 2100. And this is shown relative to the average from 1960 to 1990. And so you can see that the temperature increase in some places is close to 8 degrees. The graph over here is illustrating to us average temperature change, right? Global temperature change. But you can see here that it's not the same everywhere. So again, the northern hemisphere is where we tend to see the strongest temperature change, again, because of solar insolation. But there's also here some parts of South America where we have really extreme temperature changes. The oceans, we don't see as significant of a change because of the difference between albedo in the oceans and the land. But everywhere temperature is going up, somewhere between 1 degree to 8 degrees. So super problematic. So why do we worry about this so much then? Why can't we just get used to it being hotter and just kind of move on with life? Well, the answer to that is because, when you heat the earth, and you change the climate of the Earth substantially, there are going to be things that happen that result from that change. A lot of what we will talk about when it comes to climate change is sea level rise, and that is tied directly to the fact that if you heat up the Earth, you melt the ice turns into water, right? It goes into the oceans, and the oceans rise. We have gobs of data from the last several centuries since we've been paying attention to this, since we've had satellites or since we've had cameras that show us that this is happening, and this is happening in a very concerning way already. This image here is showing you the Canadian Arctic. So this is Greenland and then the Canadian Arctic ice sheet, which during the winter is covered completely with ice, or used to be at least. So here's an image of what that looked like in 1988. And still, even in 1988, we'd had some climate change already, but not significantly. So in 1988, you can see that most of the sea ice here was relatively old, meaning it had been around for a very long time. And that's what this map is actually showing, the age of the ice. So how long had it been present as a solid? So most of that had been around for 4 to 5 years, meaning that it doesn't melt, right? It's relatively thick and it doesn't melt. If we look at 2013, so right, in the last, 7 years or so, 7 years ago, you can see that the majority of that ice has melted, and what is left, right, is much, much smaller. Most of that ice that is left, only a little bit of it is 4 or 5 years old. Most of it is 2 or 3 years old. And then some of it has just disappeared completely and melted away. So that ice is melting. That adds a substantial amount of water to the oceans. We see the same thing with glaciers. You'll see pictures of this all the time. It's one of the best ways to illustrate climate change to people, is to go to a place where we have a picture from the early 1900s of a glacier. Go back there today, and does that glacier exist? And the answer to that is almost no. Now, glaciers do move forward and retreat, right? That's part of their pattern. So they do retreat a little bit during warmer periods, but they tend to be pretty long-term objects or pieces of material, basically, as long as you have a coolish temperature and you can maintain them. So I think this is a picture from Alaska. I'm not positive, but I think this is an Alaskan glacier. Here's an image in 1913. Here's that same valley in the year 2012, and that glacier is completely gone. And we see that over and over again in different places. So why does it matter if sea level rises, right? Why is that so problematic? Well, one of the things that you all did in lab last week when you did this last lab on climate change was an exercise about how many people live close to a coastal area or live on the coast in the United States in some of the major cities. And what we see is that, 40% of the world's population lives within 100 kilometers of the coast. That's just the way that societies have built up. It's useful to be close to the coast if you are people who fish, right? If that's kind of how your population grew from fishing, right? You need to be near the water. The temperature is usually a little bit more moderate, perhaps, along the water. And so there are a lot of reasons why people have kind of, moved to the coast or been drawn to the coast, not just the United States, but of other places as well. So that's where a lot of the world's population happens to live. And so that's a problem because when you melt ice, you take that ice that was a solid, right? It turns into a liquid, it goes into the ocean. And so the sea level rises. And so that means that the coast is actually changing, right? What we talk about as the coast today is just the coast as we know it. It's been that way for a very, very long time. But if we were to put more water into the oceans, then the coast would move inland because the sea level would rise. This particular image here illustrates what that would look like. And I forget, I think this is assuming all of the ice melts or in Greenland, or a significant amount, maybe 80% of the ice melts up in Greenland. And so you can see just how much water would now cover coastal cities. And so here we're looking primarily at the red, so that would be the deepest. And so a lot of the North Carolina coast, the South Carolina coast, much of Florida in this particular model is now underwater. New Orleans, right? That the southern part of Louisiana here, where I went to school. I love New Orleans so much, but New Orleans would basically be completely underwater. A lot of other places going down into the Yucatan Peninsula, and so it would have a very, very extreme effect on that population. And again, that's problematic because that means people have to move. Like, you can't continue to live on the coast if your house has been submerged underwater. If it's not land anymore, it's, you know, part of the ocean. And so all those people would have to be moved somewhere. And again, in lab last week, you did that exercise where you looked at how much would it cost to do that. And it's a significant amount of money. Billions and millions of dollars would have to be put into moving people, into relocating people, when instead, you know, we could take and we could put those billions of dollars perhaps now into things like clean energy, and that would, you know, solve a bit of our problem. So I'm going to click on this link here. This is a real fun quiz. You're probably thinking quizzes can't be fun. This is a really interesting quiz from the New York Times that illustrates, I think this is 170 feet. Yeah, so this is assuming that there is a sea level rise of 170 feet. And what it does is shows you the new shape, right, of a state based on that sea level rise. And so this would be a little hard to do with everybody muted and out there in Zoom land. But for example, this state here, I don't know if anybody can recognize it, but is actually New Jersey, and what New Jersey would look like with 170 feet of sea level rise. And so you can see all of the big cities in New Jersey are now completely underwater. They would be part of the ocean, so it's not land anymore. And everybody that lived in Atlantic City and Trenton and Princeton, you know, very like large population areas, would then have to move into the more inner parts of New Jersey because there would be, you know, they'd be underwater. This, I believe, is either Alabama or Mississippi, Alabama. And so in this case, Mobile would be completely underwater. And what's happened here is that the sea level rise has then flowed into the stream system in Alabama. And we see the same thing again in Mississippi, Louisiana. And so flooding inner areas of the state as well. So it's not just a coastal problem, it's a problem anywhere you have water that is connected to the ocean. I don't know if anybody can guess what this is. This is the only thing that's left of this state. So this whole area here is underwater. You might guess that this is Florida. And so 170 feet of sea level rise would just leave like teeny weeny, basically little islands here. Like they'd be, you know, parts of Alabama and Georgia sticking out of the water. It would be completely underwater. This is Louisiana. Louisiana, again, would be one of the coastal states that would be most affected by sea level rise. New Orleans is already below sea level. It's a very, very low in terms of topography. And because we have the Mississippi River, such a large river system, that river actually would flood the majority of the state if we had sea level rise. This is South Carolina, and it's always easy for me to tell this one because it looks exactly the same, but there's a substantial amount of South Carolina that's missing. Even Columbia, which is smack dab in the middle of South Carolina, would be completely flooded or almost completely flooded by water with 170 feet of sea level rise. Charleston, Myrtle Beach, big vacation spots for people who live in the South, completely underwater. This is North Carolina. And again, you see about the same amount of North Carolina, and South Carolina would be flooded. So Wilmington, Raleigh, and Fayetteville would be on the coast now. This is Mississippi, I believe. Right, so a lot of Mississippi flooded. This part here is thanks to Louisiana, right? But a lot of Mississippi flooded as well. I forget what this one is. It's Rhode Island or Delaware, no, Massachusetts. Looks very different, right? Because you lose Cape Cod completely. And Boston would be completely underwater, and even Springfield, right? You think you'd be safe in Springfield because look how far away from the ocean you are, but not, in fact, you are not because of the river system. I forget what this one is. This is Rhode Island. So you can see Providence, Kingston, and Newport all completely underwater. And this is Maryland. I think, where's my thing here? Yeah, Maryland. And so Baltimore is now completely underwater. And so you've got a little bit of land left. So it's really fascinating to think of how the coast of different cities would change with sea level rise, and it is not insignificant, right? This is a big problem, and the population displacement is why that is a problem for humanity. So another consequence of climate change is extreme weather events. I think this is a good time to talk about what the difference between climate and weather is. This is another thing that I hope that if you remember anything from geology, like, you know, about the difference between a theory and a scientific theory, this is another thing that I would really want you to remember, because this will come up all the time. People do not understand the difference between weather and climate. And so we'll say things that are not true because of that misunderstanding. So here we go. When we talk about weather, what we mean are conditions at a specific time and place. Like yesterday, for example, for those of you who were on campus, you'll know this. If you're at home, you won't. But we had really bad thunderstorms, oddly, in November, yesterday here in Waterville. And so the weather yesterday for Waterville was rainy and warmer than usual, just a tad bit. That was the weather. That was not the weather in Portland. That was not the weather where my family is in Georgia. I think it was nice and sunny. It was probably in the 60s, even maybe the 50s or the 60s. But weather is a specific time and place, and it varies all the time. And so we talk about the weather forecast for the next week. It's a short-term kind of thing. So what is the temperature and precipitation like now in this one place? That's your weather. When we talk about climate, we mean a range of weather conditions and seasonal variability, okay, over decades. So this is not something that is short-term. This is something that we have looked at and we have data for over a very, very long period of time. Like we might, for example, describe the climate of Maine as being, let's say, having pretty temperate or pretty moderate summers, but cold and snowy winters. And that's kind of the climate, like the region or the climate of this particular region. The climate of Georgia would be different, right? It's much, much hotter in the summer. The winters are shorter and not as extreme. So the climate is different, but I can say, you know, because we have all this data, we know what the climate of Maine is going to be. I can't predict how much snow we're going to get necessarily, or if it's going to be a slightly warmer summer than usual, but we have an idea of what it will probably be like within a specific range because of that long-term data. So it's longer term and it's broader, like broader regions. So Portland and Waterville, and maybe even like all the way down to Boston, have a similar climate range. Okay, not exactly the same, but the climate's similar. So when we talk about climate change, we're not talking about weather, right? We're talking about changes that have occurred over a long enough period of time that there is a new normal, if you will, right, in terms of the climate. So let's say, for example, 20 years past, I'll be at Colby for probably another 20 years, at least 20, 25 years. Maybe by the time I retire, the climate of Maine has changed enough so that we don't see the, maybe the winters are a little less extreme. Maybe it's gotten to a point where it's noticeably hotter in the summer, or the summer feels a little bit longer. And if that's the case, then we can say, okay, over the last 20 years, there's been this significant change. We haven't necessarily moved into a completely different climate realm, but there's changes that we can notice in the long-term climate. And so it's a long-term kind of observation. So, you know, people will say, like, Trump has done this before. You know, I think maybe once on New Year's Eve, it was very, very cold in New York City. And he tweeted, of course, as he's known to do, about, oh, well, it's super cold in New York City and the rest of the Northeast. Climate change is fake, right? How can climate change be happening if it's very, very cold tonight? Well, it's very, very cold tonight because that's the weather, right? It happens to be very, very cold. You can have an extremely cold day in a year that is the hottest recorded temperature on Earth, right? That is not an impossible thing to do. You still have climate variability. It's still going to be cold in the winter and hot in the summer. What we're looking at is for long-term change. Okay, so keep that in mind. Climate and weather are not the same thing. So one of the things that we see in terms of this, this extreme weather people talk about a lot is hurricanes. And I think that's a thing that's becoming a little bit more obvious the longer and longer we go. is that if we look back in time and we start to compare what is becoming the new normal in hurricane season to what we used to see, what we see now is that hurricanes are occurring more often. The hurricane season has lengthened, right? So we see hurricanes later into the year than we ever have before. And the storms are becoming more extreme. So we see more Category 3 and 4 and 5 hurricanes, which are the stronger category hurricanes, than we used to. And so this is illustrated in this figure here. So going from 1967 to 2018. And if you kind of look like right down the middle and compare the left-hand side to the right-hand side, it's obvious that there are more hurricanes and there are stronger hurricanes in more recent time, which is the right-hand side, than there is on the left-hand side. So that is the thing that's happening. And that, again, the reason that that occurs is because hurricanes are driven by warm water in the oceans. That's why there's a hurricane season. We think about the Atlantic and the Gulf of Mexico. When does it get warm? It gets warm in the summer or the spring, or probably like spring, usually to early fall. And that's when hurricane season happens to be. But now hurricane season is extending and we're having hurricanes later into the year. Like even November, I think there was one recently, maybe a week or two ago, that we never have seen before because the ocean water is staying warmer longer than it used to. And so that warm ocean water is fueling the hurricanes. So if the oceans continue to get hotter, we'll have more and more hurricanes. They'll happen more often and they're going to be more intense. And so that's especially problematic for these cities like New Orleans or like Houston or Galveston that are on the coast and very susceptible to flooding and to storm surge from those kinds of hurricanes, those kinds of events, weather events. Another thing that we see is changes in long-term weather patterns. Again, that kind of talking about how when we're changing climate long-term, we would expect then to see the weather, like the long-term weather pattern starts to change. One of the things in particular we can look at is the amount of precipitation we might expect to see. And so, for example, I think we can see this extremely well even now, right? If we look at the Southwest, California, right, Nevada, Arizona, those are places that have been having droughts, very extreme droughts, most summers for the last 5 summers or so, maybe even longer ago than that. Like every summer you hear about terrible, terrible forest fires, particularly in California this year, because it is so dry. And if it's dry, it's so very easy for the forest to catch on fire. And so these precipitation patterns that we see is that in places that are already dry, they're going to get drier, as we see in the American Southwest. So droughts would be more common. Now, in places like the Northeast, where we have a lot of precipitation, strangely, like this is kind of counterintuitive, but what we would actually start to expect to see is more precipitation again, because we have the extreme. So we have extreme drought or we have extreme precipitation. So we would expect then the winters to, or maybe even the summers, right, to be wetter than they used to be. And so we might expect to see more snow, right? Doesn't mean it necessarily has to be colder, because you can still have snow when it's 30 degrees. It doesn't have to be 10 or 0 degrees to have snow, but it's snowier, maybe for longer periods of time. And in the Southwest, it's drier. So again, problematic. That changes, you know, when you have droughts or when you have periods of prolonged wetness, it changes plant productivity, which could lead to famine. You could get parasites, you know, diseases can spread, species can die off when you have, you know, these kinds of things taking place. So these long-term weather patterns have big effects again on humanity. It's not just the thing that's happening that doesn't affect us, because it affects us very profoundly. Ocean circulation could get interrupted. To remind you again about what we talked about on Thursday with the thermohaline circulation. Remember, thermohaline circulation is driven by differences in density of the water, so hot water versus cold water. So we have to have both in order for thermohaline circulation to do its thing and to carry all that heat around the ocean. And remember, another thing that thermohaline circulation does is carry oxygen in the deep oceans as well. And we talked about the fact that we think thermohaline circulation has stopped before, and that may have been the cause of the Permian extinction, which was the largest extinction ever Again, 90 to 95% of all living organisms went extinct during that particular period in time. Because thermohaline circulation stopped, the oceans warmed up. I should say the oceans warmed up, thermohaline circulation stopped as a result of that. And so that oxygen that's being carried around is not carried around anymore. Organisms in the ocean die, and then organisms in the land die because they have nothing to eat in some cases. And so again, that's a problematic thing too. So the last thing I want to mention, the last consequence of climate change is ocean acidification, which has become a thing that people have started really talking about probably more in the last decade. And it is not talked about as much as the other effects of climate change. Ocean acidification is something that occurs because of extra CO2 in the oceans. It is not driven by increased temperature. All these other things are driven by increased temperature. So we put more CO2, we increase the temperature, and these things happen. This is just an effect of literally just putting the extra CO2 into the oceans, because remember, CO2 goes back and forth between the oceans and the atmosphere. And when you put CO2 in the oceans, what you do is you increase the acidity of the ocean water. And what do we know about acidic water, right? If we think about what does acidic water do in lab that's been useful to us, well, acidic water dissolves carbonate, right? It fizzes when you put it on carbonate. So calcite, limestone, marble, all of those react to acidic acid because of that calcium carbonate in the structure that they're made of. And so there are lots of organisms, as we've talked about, in the oceans that have body parts, right, hard parts basically, that are made of calcium carbonate. And so if you put CO2 into the water, you change the pH of the water, you make it more acidic, you start to break down the hard parts of those organisms, which is, again, a problematic thing. So here is some coral in regular ocean water, so ocean water with a normal pH on the left, and here's what it looks like in acidic water. So you're destroying the parts of the organism that basically serve to protect it, and then you make it very vulnerable to other organisms or people. You know, we tend to really trample coral reefs when we are in the ocean swimming around a lot. And so it's much easier to destroy these organisms if they don't have those hard parts protecting them. So that's a problem. That doesn't necessarily like relate back as strongly to us as all of the other consequences, but is certainly a big problem for ecosystems in the ocean. Okay, so I know this all sounds very like doomsday-ish, you know, in terms of this, all these terrible things are going to happen. But the good part about this is that there are things that we can actually do to slow climate change down. I don't know that we will be able to stop it because our society is so industrialized, maybe at some point in time, hopefully. But we can certainly do some things to slow it down. What can we do? Well, the first thing we could do is decrease energy usage. USA and China in particular are not very energy efficient. And so a lot of climate change is due to our two countries. We could, you know, try to be more like Europe or try to be more like Japan, be like our European and Japanese neighbors and use less energy, and that would be helpful. In case you want some numbers, the CO2 per person, if we think about how much CO2 per person we are putting into the atmosphere in the USA, it's 5 times higher than the global average, and it's twice as high as Europe. And China is here in this bullet point because most of the recent growth in CO2 has come from Asia, and that's because as Asia has moved more towards very modern society, the population rise, the technology, like all of that has put a lot of CO2 into the atmosphere. I think the best thing to do, and I think a lot of people would agree, I imagine many of you as well, in order to move away, like to try to get ourselves out of the climate change position that we are in, would be to switch to renewable energy. The majority of the energy in the United States and in the broader world, but in the United States in particular, comes from burning coal. And when you burn coal, you put CO2 into the atmosphere. That's just the way that it goes. You know, for every, and petroleum, like petroleum is the same way, fossil fuels are the same way. For every 50 kilogram tank of gas, 150 kilograms of CO2 are produced. So all of these things that we do in our everyday life is putting CO2 into the atmosphere. So, and some of those things we can't necessarily get rid of completely. I mean, people need to drive, people need, you know, smartwatches and phones and computers and all of that, you know, in some way is contributing to this. But, you know, we could certainly change the way we use our energy and move away from a coal-based energy to solar energy, for example, or to wind energy. Europe has done that exceptionally well. They're kind of very progressive in terms of wind energy in particular. I think Germany is what I'm thinking of in particular, but do a very good job of harnessing those other kinds of energies. If we could put the money into developing those, I mean, and it would take a lot, right? We're not Germany, which is a small country, right? And we're not even just Europe, right? The United States is very large. It's a very large landmass. It's very highly populated. So it would take a lot of effort. But certainly if we were willing to invest in these energies, if people put solar panels on their houses and we put more windmills up in places, there was a ton of windmills in Illinois when we lived there. If we were able to do that everywhere, right, and to invest in these other strategies, that would have a huge impact on climate change. Another thing that's really interesting that I want to just mention briefly is carbon capture. Carbon capture, there's a video here, I won't have time to show it, but I'll put it on Moodle and you can watch it, that explains how carbon capture works, and I think it does this very well. But carbon capture is a technology that actually takes the carbon as it is being separated from the coal, let's say, for example, and separates it and puts it somewhere else. So it finds another reservoir to store the carbon as opposed to putting it into the atmosphere, because that's where it's going to go naturally. Like we're burning it, we put it into the atmosphere. So if we could physically separate the carbon, the CO2, in that process and find somewhere to put it, like put it away, like put it in a shoebox and put it away in the closet, then we would be moving towards like making real extreme progress and changing the way that we do things, like in putting less CO2 into the atmosphere. A couple of places that people think about putting the extra CO2 is into rock, for example. So what if we could build pipes, and this is actually not a crazy idea, it can be done, right? We could pipe the CO2 into layers of rock that are under permeable layers, so the CO2 can't escape, put it back into more limestone, right? There are ways you can do this in reservoirs where you can put the CO2 to keep it out of the atmosphere. And so it's really interesting, so I recommend that video. So a question then is, if we know that we can do all of these things to make climate change slow down, right, to kind of stop the path that we are on, why do we not do it? And there are some really funny clips here from the Stephen Colbert show and Jon Stewart. And again, I don't have time to show them, but I would highly recommend you go back in the PDF here and click on those links and watch them. That talks about why this is so problematic. And this is where we start to, cross from geology into politics or into government. Because, if we want to do things, if we want to make actual progress, like, developing carbon sequestration or really moving forward with clean energy in the United States, we have to have the money to do it. And who approves money for things? Well, Congress approves money for things. And the problem is that you are probably all very well familiar with this, that we have a lot of policymakers, a lot of governmental officials who don't believe that climate change is true. They don't believe that it's really happening. Either they honestly don't believe it, they don't understand the science well enough to understand why it has to be true, or they're getting money from donors who are making money off these things, and so they're going to pretend like it's not happening. So who knows if they're pretending or if they don't understand. But there are so many people, your governmental representatives in the Senate and the House of Representatives, president, right, and the vice president currently, who do not believe that climate change is real. And so people don't believe that it's real. They're not going to invest in alternative energies. This webpage here, I'm just going to bring it up so you can take a look at it. I would recommend that hopefully it's going to open here in a minute. I would recommend that you just take a minute to look at this website. It's called Skeptical Science. And this particular part of the webpage here will actually take you to a list or images, right, of senators, representatives. They're basically all Republicans because this is a very political issue. It is Republicans who tend to deny climate change. And you can click on them and it'll bring up some random things that they've said about climate change. So Mitch McConnell's not very excited. There was one with Mitt Romney, Herman Cain. But you can click on these different people and it will tell you some of the things that they've said about climate change. There's Mitt Romney. What did he say? He says a lot that he thinks the world is getting hotter, but he doesn't know if it's mostly caused by humans. And so he's not willing to spend trillions of dollars on something that he doesn't know the answer to. And that's the thing that you will hear a lot. I'm not an expert, but, right? Well, if you're not an expert, then what you should do, right, just in general, is listen to people who are the experts, right? If I have a question about anthropology, I go to an anthropologist. You know, I don't go to a random person on the internet that doesn't have any understanding of anthropology. So it's important to listen to the experts, and I think that Jon Stewart and Stephen Colbert do a really good job of illustrating how crazy that is. Okay, so let me stop the share here. And so that's all I've got. We don't have a lot of time, so I'm not going, we only have 5 minutes, so I'm not going to ask you to do this last exercise, but when you download the PDF, if you take a look at it, the last page says in-class assignment, and it has a bunch of quotes. A lot of these are real quotes that people have said to me online. Many of them are from a cousin of mine who I really do not enjoy, but he gives great quotes about bad science. And so I steal his quotes and think about how you would respond to these. Like, I think that's an interesting thing to think about, because these are things that you're going to hear, right, in your life. And, you know, as a good steward, like as a good citizen of society, I would hope that, you know, you'll be able to respond to some of these ways, some of these, not perfectly necessarily, but to say, you know, listen, that's not true, or let me explain to you what I do know about climate change and why this is important. And maybe we'll start to make a little bit of progress. Okay, but that's all I've got. Are there any questions? Anybody? Nothing? Okay, we've got 5 minutes. So what I want to do actually in the last 5 minutes, since we started the semester with a little talk about why you should study geology, I decided we'll end the semester with me showing you, go back to my screen here, why I love geology. So yesterday I put together just a few slides here. And again, I'll just take the last 5 minutes to do this, about some of the reasons that I love geology. Why am I so geeked out about geology? So some of these are sciencey and some of them are not necessarily. I really, really love beautiful minerals. Like, I just think that they're gorgeous. They get me so excited. I look at these things and think about how they can form. And it's like, and I know a lot of the science about how they form, you know, obviously, but it's still like almost a mystery that, you know, nature can make something so beautiful. The left-hand side here is chromium diopside, and diopside is a pyroxene. And you did not see that particular pyroxene, but you have probably forgotten all the minerals now, and that's fine, but you did see some pyroxene minerals in lab. But I think that color green is just the most beautiful color. This crystal here on the left is little crystals of garnet, and I think that that's barite flowers is what you call them, but they're made out of barite, the mineral barite. And like, that's a real thing. Like, nature just made that. And I think that that's fascinating. It's just beautiful. It blows my mind. I also really love giant slabs of rocks. I don't know this person. This person is a geologist on Twitter that I have encountered that shared these pictures. So her and her spouse went to go look for some countertops and went to this most amazing place that has the most interesting rocks I think I've ever seen, and took a bunch of pictures of them, because as a geologist, that's what you have to do, right? You have to take a picture of all these rocks that you can see. And so these two are my favorite. So the one at the top right, you can see this is actually, it's sedimentary rock that's been faulted in multiple places. Like, she's pointing to one fault, but then there's 1, 2, 3 more in the image. Actually, yeah, there's 3 more that I can see. And you can look, or there's a 4th one down here too at the very, very bottom. It's kind of faulted just in like a V shape. I think that's fascinating. Like, all those little faults right together, and the colors are just beautiful. But this one on the left, it geeked me out so much, I can't even describe to you how excited I was about this rock. I just want to buy it, not as a countertop, but just to put it in my house and stare at all the time. It's so beautiful. This is columnar basalt that's been cut vertical. So you would be looking down on top of all the columns. Oops, sorry. And the columns have been replaced by silica. So it's silica replaced basalt, which blows my mind. And I think that's the coolest thing ever. And I just really want both of those just as big chunks to put up in my house somewhere. We wouldn't really work in our kitchen, but I just want pieces of them. I also really love geology memes. I like memes a lot. If you ever look at my door, you'll see that there are lots of memes on my door. I particularly enjoy memes about meteorites because I get a lot of emails from people or phone calls from people who think they have found a meteorite, and it is never, ever, ever a meteorite. And so that's a big joke. I love the Oprah meme here about assimilation. Remember, we talked about magma assimilation. You get assimilated and you get assimilated. Everybody gets assimilated. So Oprah's very excited about that. Bernie Sanders is outraged that 1% of streams contain 90% of the stream water in the country. So those are fun. And diamonds, I didn't get a chance to tell you guys that I really just don't care for diamonds. It's a whole story. If you ever take mineralogy or earth materials, I'll tell you about it. But I think this is funny because they're just unstable graphite. Another thing that I love is creative science at home. You know, we talked about the fact that when I bake stuff, if I can turn it into an example in class, it gets me very excited. Here's the fancy cake, not a fancy cake, but here's the cake that I made that is a perfect example, and not on purpose at all, but a really, really great example of extension that is caused by, you know, an increase in volume. So that's just amazing. This is a cake. I made a layered cake, just decided to make a colored pound cake. And I cut it in half, and it looks like it's got layers, and it looks like it's got little magma chambers moving up towards the surface, and I thought that was fascinating. I did not do this over here on the left. I found this on the internet. Somebody actually did a very simple one, and some really geeky geologist came back and was like, no, let me do a better one for you. And so this is a subduction zone illustrated with towels. Fascinating. I'll put this online so you can go back and look at it, but I want to finish up really quickly. I love cats, using cats in geology. I think that's hilarious. It kind of goes along with my love of geology memes. So here's H2O. Here's a cat illustrating a hanging wall. I wish I had found this when I was actually teaching that in class. I would have used it for you. Here's a subducting cat underneath a mountain. All of these are very funny to me. I really geek out over geology tattoos. I think science tattoos are really, really fascinating to me. This tattoo over here on the left is part of a map. That was a map that someone made as part of their master's dissertation. So they made this map. They mapped this geologic area and got a tattoo of it. This person here, again, these are random people from the internet. I don't know them. Had the geologic timescale tattooed on their arm, and that blows my mind that you'd have the geologic timescale tattooed on your arm, but they did, and that's amazing. So those are some of the things that I love in geology, and so I wanted to share those with you. Just so you have an idea of, you know, in the semester was something necessarily that's not climate change. There's a cat. Lucy's cat's there. Hey, Lucy's cat. I love that cat. So that's all I've got, guys. Thanks so much for a really great semester. The final exam is posted on Moodle. If you have any questions about that, don't hesitate to email me. There are 2 questions to choose from. You have to write a 3-page response. There are lots of detailed instructions about what that should look like and the formatting and how you should turn that in. That is due by 9 p.m. on December 2nd, and December 2nd is the actual day of your final exam. If we were to have one in class, it was a 1:30 p.m. time on December 2nd. So I'm giving you till about 9 p.m. that night. I would recommend not spending any more time on the final than you would if you were taking the final and studying for it. So just because it's a take-home exam and because it's an essay doesn't mean that you need to spend 3 times as much amount of time as you would otherwise. If you were going to spend 4 hours studying and 2 hours taking the exam, then give yourself 6 hours to do this. Turn it out. I'll be excited to read your answers, but both of the questions are about material from the second half of class. One is geared a little bit more towards superficial processes and superficial evolution in sedimentary environments, and that's using Mars and Earth as a comparison. And the other is geared more towards atmospheric evolution and climate, and that's using Mars and Venus as a comparison. So you get to pick which one you want to do. Just be sure to follow the instructions, and I'll be happy and excited to read those. So that's all I got, though. Thanks so much for coming, everybody. Everybody stuck it out to the end here too. And thanks for showing me your cat, Lucy. That was very exciting. So anyway, if you have any questions, you know where to find me. Happy holidays. Have a restful break, and I hope to see you guys around campus in January or in the spring. Okay. So everyone take care. Thanks for a great semester. I had a fantastic time. All right. Bye, everybody.
Thank you.
Bye. Thanks, Lucy.
Yeah.
Thanks, Alana.
They say.
Thanks, guys. Thanks, Robbie.
Thank you.
Thanks, James.